Hey guys, how's it going? So I'm practicing radial algorithms and I found this cool problem which requires some intuition and some cool proof. So I thought I would create a video on this, and this would be the first problem for the Creedis problem series that I'll be creating on YouTube. So let's start with this problem. So first we'll go through the problem statement, then we will see some examples, and then I will describe the solution, and finally we will go to the proof. So yeah, let's start with the problem statement. Before any of that, I would strongly suggest you to go practice this problem on Codeforces first, so that you can get more from this video. I'll provide the link to in the description. Yeah, so you can pause the video right now, and let's meet again. Yeah, so were you successful? If yes, then congratulations. If not, then yeah, we'll head to the solution. So first, let's go through the problem statement. So there are three kinds of balloons given: red, green, and blue, and we require three balloons to decorate one table. So let's say there are five red balloons, five green, and five blue. Then we can decorate five tables. So there is one condition for the decoration, that is, all three balloons can't be of the same color. So all three balloons that we require to decorate the table can't be of the same color. So for example, we can have RGB, RR, and G, but we can't have all the balloons as blue. Similar, we can't have all of the balloons as red or green. So the ask of the problem is find out max number of tables that we can decorate. Yeah, so this is the problem statement, and now we can head to examples. So these are examples I picked up from the problem itself. So these are given here. So let's go through the first example. So for the first, like they have explained itself, like there are five red balloons, four green, and three blue balloons, and these are the four tables we can decorate in this way. For example, the first will be RGG, second will be GBB, third will be BRR, and fourth will be RRG. So the answer given is 4. And for second, it's easy to see that the solution, that the answer to the problem is 1, because we can take one red balloon, one green, and one blue. And for the third, we can see that the answer is 2, because if we sum all of these, so it will come out 6 plus 2, 8. So the remainder of 8 remainder 3 is 2. And yeah, so 2 balloons will be left out anyways, whatever case we try, and so the answer is 2, because 8 by 2 is 8 by 3 is 2. Okay, so these are the examples, and we can head to the solution now. So first, we can ask some questions before moving to the proper solution. So first question would be like, what would be the best case? So the best case I could think of was like if when R equals to G equals to B. So in this case, we will decorate tables by picking one color of each balloon at one time. So we will create R tables in this case, or G tables, as all are equal. So this is the best case. And second question we can ask is, what can we inference from the best case? So the thing is, it was just my intuition that whenever these values are nearly equal, that would be better than other case, like when these are far apart. So for example, if we have 5, 4, 3, and if we have 5, 5, 2. So in this case, this case is better, and this is not. So we try to see like if we can move to this case. So this is the inference that I made from the best case, that if all are nearly equal, then we can decorate the maximum tables. And third is, what would be an extreme case? So extreme case I could think of was, let's say R is too much greater than G or B. In that case, we can always use two balloons from red and one balloon from G or B. So in this case, the answer would be G plus B. But what would be the condition that we can say that this is an extreme case? So the condition will be like we always want to use one balloon for G or B and two balloons for red or two balloons from red. So if G plus B, 2 times G plus B is less than equal to R, then this would be an extreme case, because in this case we can always use two balloons from red and one balloon from green or blue, and this will give us the answer G plus B. Okay, so now coming to the answer, here we have made one guess that the answer can be G plus B. It will be in case of when 2 times G plus B is less than equal to R. Yeah, and the answer can be like, we can sort it out. Let's say G is greater than B or R. In this case, the answer would be 2 R plus B. So this is just like this is not just one case. There will be three cases, whether blue balloons are very huge in number, or red balloons are very huge in number, or green balloons are very huge in number. So the second case is like I just made a guess that the answer would be R plus G plus B upon 3. That would be the answer. So I submitted this solution like taking minimum of both of these values, G minimum of this value and G plus B, assuming that R is greater than G greater than B. Yeah. Now like I submitted in on Codeforces and it code AC. So now remaining is the proof. So let's head to the proof now. So for the solution, I had assumed that the answer would be minimum of R plus G plus B upon 3 or G plus B in case when R greater than G greater than B, right? So why did I assume that this can be a solution? So it was just my intuition that whenever the condition that 2 times G plus B is greater than equals to R, then in this case we can always like match the most balloons and get the maximum table, and leaving remainder that would remain by R plus G percent 3, remainder 3. Yeah. So how can we prove this now? Let's see. So we can try to make some diagrams and make some cases here. So for example, let's say we will try to solve it for R greater than G greater than B, and other cases are similar, like G greater than R greater than B, etc. Yeah, so let's solve with this. Let's prove this for this condition. So we have 3 buildings. I will draw with red. So these are the red balls, and these are the green balls, and these are the blue. Sorry, I'm saying balls, it's balloons. So these are the blue balloons. Yeah. So here, like I created, and we can think of creating an algorithm so that we can achieve this answer, R plus G plus B greater than 3. This is easy to understand why it is in the answer. So we can think of an algorithm so that we can come to this answer. Let's think of the algorithm. So I made an inference in the questions, like if the case there were two cases that if the difference between the balloons is minimal, then that would be a far better case than the other one. So we can use this thing to create an algorithm. So let's say we have R, we have G, we have B. and we have r greater than g greater than v. So our step 1 would be like we will take 2 balloons from r and 1 from g. So at each step we will see we will set these two, like whichever is the greater. Let's say after this step g became greater than r and greater than v. So in this case we will take 2g and 1r. So whatever is the case, whichever is the highest number, we will take 2 of them, and the second greatest we will take 1 from them. So this is the general hypothesis of the algorithm, and we will use this until we reach a case where like all are nearly equal. I'm saying nearly equal, it means that the difference between maximum and minimum is at most 1, not greater than 1. Yeah. So let's see how we can use this algorithm to move forward. So in this case, like we will take 2 from red and 1 from green. So we will do this again and again until there are 2 options left. Like we will reach either of these 2 conditions first. So first condition would be that the red became nearly equal to green. So nearly equal means the difference between red and green is less than equal to 1. And blue still is the smaller one. Okay. And the second case would be that the green reach to red first before red can reach to green. Yes. So in this case the red would be highest again, and green would be nearly equal to blue. Yeah. So these are nearly equal. In this case these were the nearly equal. And there is third case also, but that would get covered, like all of these gets nearly equaled like this. So the difference between them is at most 1. Yeah. So we can solve like this case. We can see that what would be the answer in this case. So whenever we reach this condition, we will start taking one balloon from each of the colors, and we will do this until all of the like until there is one ball color which is 0. So in this case the remainder will be less than or less than 3, because there are 2 cases in here where the maximum minus minimum is less than equal to 1. When 2 are similar, let's say, and 1 is smaller, in this case the remainder will be 2. And the other case is when 1 is higher and 2 are equal. In this case the remainder will be 1. Yeah. So the remainder will remain less than 3 in this case, and we have achieved the best like the maximum number of tables in this case, because we can anyway use 3 balloons at a time, and the remainder is less than 3, so we can't use rest of the balloons. Yeah. So now we can come to this case. So in this case red and green were equal. So what will happen now is they will like whatever is higher we will use 2 of them, and the rest will the second greatest will use 1. So they will like decrease 1 by 1 at a time. For example, let's say green were 5, blue were 4, and red were 2. Sorry, red were 4, green were 5, and blue were 2. So in this case, like we will use 2 from 5, we will reach this case, and 1 from 4 will reach here. Yeah. And now these are equal, so we will use any one of them. And since the difference is less than equal, we reach this use case. But yeah, we can like these will take turns, like first this will take two from this one, will take one from this one, in the next turn will take two from this, one from this one, and sometimes they become equal, perfect equal, sometimes there is difference of one, sometimes like this is higher, this is lower, but the difference will remain less than equal to 1 each time. And after some time they will reach like at this stage where red, green and blue are nearly equal. The difference is less than equal to 1, which is similar to this case. Yeah, this case. And we can follow the same algorithm that we followed here. Okay, so we can now discuss this use case, what will happen in this one. Now in this case, like the red were the largest, green and blue were nearly equal, right? Actually these were actually equal, because we were only taking from green, so it will anyway reach at some point equal to blue. Yeah, so these will be totally equal. And now there will be two cases from here, like we will each time take two from here, and like in first run, let's say we will take one from this, in the second run we will take one from this, so these will decrease one by one. So there will come two cases, either the three buildings will become nearly equal, and this will reach the same case as this one, or the second case is red will remain higher, and blue and green will become 0. Yeah, so this is the case where we were saying that answer will be g plus b, and the answer indeed is g plus b in this case. Yeah, so this is the proof, like we can achieve the maximum number of tables with this algorithm. So we have found algorithm that works for this use case, and we can say that this is a proof as we have found a algorithm. Yeah, so that's it for this problem, guys. If you like this video, hit the subscribe button and the bell icon so you never miss an update.